to this video. My name is Muhammad Waqas, and in this video, we're going to discuss the general concepts of general physics 2, which is from University Physics, from chapter, I think, 21, chapter 21 to 29. So, this is the review video of the concept what you have learned in this course. So we're going to do it quickly so that you can learn this concept, uh, all the basic concept related to this course, and then you will able to ready for yourself for the problem solving session, and finally for the final term exam. So, the first concept what we learn in this course is the electrostatics, which means charges at rest. So, what is the charge? Charge, charge, charge is a fundamental entity of the nature. And you know that everything is made up of uh, atoms and molecules. So, atoms and molecules. So, atom composed of two things like the electrons and the nucleus, and then nucleus is composed of the protons and the neutrons. So electrons are the negative charge particles, and the proton is the positive charge particle, and the neutron is the neutral particle. It has no charge. So these are the fundamental particles in which we express the bodies. So when we say that when the object is positively charged, it means it has lost electrons. It has lost electrons. And if the object is negatively charged, which means it's gain electrons. So different bodies can be charged. So how can you charge a body? You can charge a body by a friction. Okay, or you rub a silk or glass, so or cat fur, so you can charge a body. So you transfer the electron onto the body or remove the electron from the one body to another body. The next concept what we learned in this course is the Coulomb's law. So Coulomb's law about describes the describe the force of between the 2 point charges which are separated by a distance. So these 2 point charges q1 and q2, and they are separated by a distance r from their center. Then this law is q1 q2 is a magnitude over r squared. This is the r distance. So if we increase the distance, if we increase the charges distance, which means we are increasing r, so force is decreasing. If we increasing the charges, it means we are increasing the force. And this is the permittivity constant. K is a constant which is nothing but 1 over 4 pi epsilon naught. And epsilon naught is the relative permittivity of free space, which is nothing but 8.85 10 raised to power minus 12 Newton meter square per coulomb square. And K is a constant which is 9 into 10 to the power 9 Newton meter square per coulomb square. So this is the Coulomb's law, which states the force between the 2 point charges. And if you have many point charges, you can add the forces, sum of all forces, then F1, F2, F3, and so on. And this is the superposition principle. Superposition principle. Now, so if you have a charge, have a point charge or a positive charge, then in an area or a vicinity, it can attract or repel any other charges. So the electric field at a point is electric field at a point is nothing but the force per unit charge, is the force per unit charge, or a positive point charge. If you place a positive point charge, if this is a positive, the field lines is like this. So every charge has its an area or a vicinity in which it attracts or repels any other charge due to the electric field. An electric field is defined as force per unit charge, which having a unit Newton per coulomb. So if you want to calculate the electric field due to a point charge, so this is the expression for the electric field due to point charge, which is E ke, which is the constant, q over r square, and r is this distance. This is q, and this is another small q or q prime. So you calculate the force per unit charge on this charge. So it is the electric field, and this is the electric field due to point charge. Then, so the direction is radially outward for a positive charge, and electric field radially outward for a positive charge. And if it become a negative charge, this is negative charge, and we want to find out at this point, so it is radially inward. So radially outward, and this is radially inward. Okay, so electric field lines originate from positive charge and terminate on a negative charge. Okay, so the density of the electric field lines increase the strength of the charge. So if it has like 3q and this is positive or negative q, so the field lines are dense over here, which means the strength of the charge, where lines are closer together and the field is strong. Okay, so it all field lines originate from positive charge and terminate on negative charge. So negative field lines has inward direction like this. And if you have stronger lines, it means the strength of the charge is there, greater strength of the charge, and has a stronger electric field. Next, we have a concept related to the flux, which is Gauss law or Gauss's law. So Gauss's law is related to the flux, which says that flux, electric flux is nothing but the electric field times the area of that. Or you can write it in terms of integral is the flux E dot dA, the total electric flux to a closed surface is the charge enclosed in it divided by the epsilon naught. So it relates to the electric flux through a closed surface to a net charge enclosed within that surface. It is particularly useful for calculating the electric fields in situations with the high symmetry. So, for example, symmetry means we have sheet of charge distributed uniformly. This is a symmetry. Then you have a line of charge, and then you have, or you have a cylinder of a charge, cylindrical, or you have a spherical shape. So in these different scenarios, there is a symmetry and the charge is uniformly distributed. So for to calculate, to apply the Gauss law, you need to have a closed Gaussian surface according to the symmetry or symmetry. So Gaussian surface, and then you calculate and apply this Gauss law, which is E dot dA to a closed surface is nothing but Q enclosed divided by the epsilon naught. And for a case for the charged cylinder, the electric field is described by this expression. Now, where phi E is the flux, E is the electric field, and dA is the differential area vector. Now move to the concept of electric potential energy. So electric potential energy of the system of three charges represented at. So the electric potential energy is represented as, if between the two charges, is K Q1 Q2 over R12, which is R12 is the distance between the two charges. So it's a scalar quantity and it is related to the work done. So the work done by the external force with the constant kinetic energy is Q times the potential difference. So this is external work, and electric potential. So we can relate to the electric potential to move a charge from infinity to that particular point, we need to do a work. So the work done per unit charge is the electric potential. And if we are moving from infinity to that particular point, infinity to that point C, so we can write it as like VC and VA. So the work done, which is stored in the terms of the potential energy, is Q times Vc minus Va. And we suppose that at infinity, the potential is zero. Because the potential for a point charge, so the potential for a point charge like this is a potential for a point charge or a conductive surface. So this is a point charge, and the electric potential due to point charge is kq over r. Okay, so the electric potential inside and outside of the conducting surface is the same, and it depends upon this r, whether it is outside or inside. So the potential difference between point outside and at the center of the surface is represented by these 2 points, the difference of the potential. Okay, so we can find the electric field by the potential by negative gradient. So if we know the potential, we can find the electric field. So gradient, if you have only one dimension, so it's just a dv over dr. So if we know the potential, for example, this is the potential for a point charge. So it is derivative with respect to r. So E will be d over dv k q over r, negative sign. So k q is a constant. So d over dv over 1 over r. So it's a derivative of 1 over r is 1 over r squared, negative 1 over r squared. So negative kq, negative 1 over r squared. And this will be positive. So kq over r squared, which is the electric field due to point charge. We have seen that. This is the electric field due to point charge. Okay. Now, capacitance. So, capacitor is an electric device, is a device, parallel plate capacitor is that stores charge. So for a capacitor, this is a symbol for the capacitor. And the capacitance of a parallel plates capacitor depends upon its geometry. It connected to a battery with the voltage V. So, so charge stored on a capacitor is Q equals to CV. And for a parallel plate capacitor, because its capacitance depends upon its geometry, so epsilon naught is the relative permittivity of free space. A is the area of the plates, and D is the distance between the plates. Okay. So if we increase the distance between the plates, capacitance go down. If we increase the area of the plates, capacitance go up. And if we put another medium inside the capacitor, which is the dielectric medium, so it also increases the capacitance of the capacitor. Okay, so we can connect this capacitor into series and parallel circuits. So for example, in parallel, circuit will be like this. Then they're connected to the battery. So this is C1, this is C2, this is C3. So in parallel, so when capacitors are connected in parallel, the voltage across each capacitor is the same. So the voltage across these each capacitor V1, which is equals to V. This is V, this is V as well, and this is V as well. And the charge, since V is the same, the capacitor with the largest capacitance will have the largest charge. So Q equals to CV. Those we have largest capacitance will have the largest charge. Okay, so in that case, so equivalent capacitors in parallel can be calculated as this: C1, C2, C3. Okay, and we can calculate the capacitance charge across each capacitor. For a series, the capacitor can be 1 to 1. Okay, so in series, the 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 charge would be the same and the potential varies. So the equivalent capacitance can be calculated as by this: 1 over C1, 1 over C2, 1 over C3. So capacitors store energy or charge. So energy stored in a capacitor is 1 half CV squared, which is Q equals to CV. So if you substitute over here V is Q by C. So 1 half C is Q by Q square by C square. So one C will be cancelled out and you will get this. And if you substitute with C, you will get this. So these three are different formulas for calculating the energy stored in a capacitor. Then if we put a dielectric medium like this, any medium, water or any dielectric medium, rubber or anything, so the capacitance is increases. So this dielectric constant increases the capacitance because the capacitance of a capacitor depends upon the geometry. So C is epsilon naught A over D, and if you change this epsilon naught with free space and you change another constant epsilon R, which is the relative dielectric constant of that relative permittivity of that particular constant, so the capacitance got increased with that. So this is all electrostatics. Now we are moving to the electrodynamics, which when the charges are in motion. So when a charges flow in a conductor, charges flow in a conductor, it produces electric current. So current is nothing but Q over T, or you can write it as dq by dt. So when charges flow to the conductor, so current will flow. So we can have two types of current. One, we have electronic current, that is flow due to the negative charge electrons, and the conventional current due to positive charge. Okay, so the drift velocity of that electron is equals to vd, which is I. N is the number of charge, Q is the charge of the electron, and A is the area of that conductor. So resistance, which is the hindrance to the flow of charge. Hindrance means it stops the charge, because when there are so many charges, so charges collide with each other and it loses its velocity, or velocity got reduced, so it produces hindrance to the flow of charge. So resistance is a hindrance to the flow of charge, and it is related to the Ohm's law, which is I equals to V over R, or you can write it as V equals to IR. Okay, so the resistance of a wire or a conductor is related to this formula, which is the resistance. L is the length of the wire, and A is the area of a wire. So if you increase the area, you are actually bigger, so you have smaller collision, which means smaller radius. Increasing the length, increasing the collision, which means increasing the resistance. So this is the resistivity, which is resistivity is the opposite of conductivity. So conductivity is a property of the metal due to which it conduct electron, which is related to the free electrons. So resistivity is related to conductivity, which is reciprocal of the conductivity. Okay, so if you have a circuit or internal resistance of the terminal of the battery, so V, if the circuit is closed, this is the potential across the the battery with the closed circuit. And for the external circuit, this is for the internal, and this is the external, which is something like Ohm's law. So power dissipated by the circuit. So this is the concept of the power. So the brightness of light bulb is directly related to the power it dissipate. So power is given by P is equals to I square R or V square over R. For example, this, if we substitute I equals to V over R, so we get P is equals to V square over R square into R. So R and R will be cancel out. So it will be V square over R. So we get this. Or power is IV. So these are all three formulas for the power. Like the capacitor, we can have a circuit element resistance. So we can connect a resistance in series like this. This is R1, R2, R3, and then they are connected to battery with a voltage V. So in a series circuit, the total resistance is higher, leading to less total current for a given voltage. So you can, the voltage across each bulb is less than the source voltage. So you have, you can add the total resistance or the equivalent resistance is just by adding the resistance, each resistance R1, R2, and R3. So the total resistance is higher, leading to the less total current for a given voltage. The voltage across each bulb is less than the source voltage as well. In parallel circuit, the equivalent resistance is calculated as this. So you can have like parallel resistance. You can have like this. This is your R1, R2, R3, and then they are connected to the battery. And the total equivalent resistance can be calculated as this. Now we have a set of two rules which is very important. That is Kirchhoff's law. So Kirchhoff's law related to the concept of current and voltage. So the sum of current entering, so the sum of current entering a junction or a junction is equals to the sum of current leaving the junction. Okay, and you can write it as like sum of all the current equals to 0. So if you have a junction, any point, so the current entering and current leaving at that particular junction is Kirchhoff's first law. Then you have, and it is related to the charge conservation. Charge conservation. Then you have Kirchhoff's loop rule. Kirchhoff's loop rule, the sum of the potential difference across any closed loop in a circuit is 0. So this is delta V equals to 0. This statement is the conservation of energy because the potential difference is related to the energy. Then you have an RC circuit, R resistance and a capacitor connected to the battery. So this is R and C. So circuit containing resistance and capacitor, the charging and discharging of a capacitor is characterized by this time constant. So this time constant at the time at which to calculate the charging or the discharging of the capacitor is related by this time constant. So this has a unit of time which is R, which is R is the resistance and C is the capacitance. So charging of a capacitor is calculated by this expression which is this is a maximum charge sometime which is denoted by Q naught, and this T and this tau is a time constant. So discharging is given by this and it's exponential process, so it will like this: charging, discharging. So Q as a function of time, Q as a function of time. So this is all about circuits. Now moving towards magnetism. So magnetism is a very ancient phenomena. So for example, you have a magnet has a north pole and a south pole, and you have bunch of iron foils. So these are attracted. Heinz Ørsted first time observed a phenomena. So when this conductor is connected to the battery, so current will flow in this conductor. So when the current is flow, the charges flow, they produce current, and this current produce a magnetic field around this conductor. So this magnetic field B is produces by the current. So when you put a charge, a moving charge in a magnetic field, so it experiences a force. So so B is a magnetic field produces in this form, and it when you place a moving charge, it experiences a force, which is this. So magnetic force. So its Q is charge, V is its velocity, charge velocity, and B. So you can write it like this as well. QVB, the cross product is sine theta. So force is maximum when the angle is 90, zero when the angle is zero. Okay. So this is the expression for the magnitude. So if you place this is the magnetic field. If you place a conductor inside the magnetic field, it experiences a magnetic force which is related to this, I L cross B sine theta. So magnetic force on a current carrying wire is magnitude is like this, ILB sine theta. So if you place a loop in a magnetic field. So this loop is tilted due to the force of on a loop. It produces a torque which is related to this. This is magnetic moment and this is B. So the torque is mu B sine theta and mu B is NIAB. Mu is NIAB. B is the sine theta. So this is a torque when you place a loop in a magnetic field. So when if you have a magnetic field, or you can like this, you can show the dot, or you can have cross. So magnetic field inside into the page is represented by this. A magnetic field out of the page is represented by this. So magnetic field. So when a charged particle is move in a move when a charged particle move in a magnetic field, you have a magnetic field, and the charged particle is coming, then this charged particle move in a circular motion, circular path, and the magnetic field is can be calculated by this formula, which is mv q over r qr, where r is the radius of that circular motion. Then we have another important concept, which is the Ampere's law. So Ampere's law says that for any closed loop, for any conductor having closed loop, closed loop integral around any closed loop is equals to the current enclosed in that loop times this. So if you remember, we have a law which is Gauss law, which says that the charge enclosed divided by So these are two most important equations for you now. So if you calculate the electric field for a straight long loop like this is the magnetic field. Sorry, magnetic field. So the magnetic field at the center of a circular loop is mu I over 2r 2r. And this is the Biot law, Biot law, which is related to the two conductor when the current is flowing into it, and the force per unit length is represented by this relation. So the magnetic field inside a uniformly current carrying cylinder can be calculated by this. And if you have a solenoid which is like this, so the magnetic field inside the solenoid is strong and very weak or nearly zero outside the solenoid. So this is the formula for the magnetic field for a solenoid. This is the form of solenoid. So B is equals to mu naught. N is a number of turns. If you increase the number of turns, magnetic field goes increases, and times the current flowing. So this is the magnetism. You can find the direction of your magnetic field using right hand rule. Right hand rule. So if you have a right hand, okay, so your curl finger will represent the direction of the magnetic field. Your thumb curl finger direction of magnetic field, thumb indicate the current, and the palm the force. Or you can use your Fleming left hand rule, which is three fingers thumb, then you have forefinger, and then the middle finger. Thumb will indicate force, forefinger represents the magnetic field, and the middle finger represents the current, like three dimension. So it is FBI, thumb, forefinger, and middle finger. So these are the concepts of what you have learned in general physics 2. So I'll see you in a next video, which will be having a past exam solution. See you and goodbye.